Okay, the last portion of chapter 27 has to do with a specific application. Okay, mathematically, first of all, however, we take a look at a torque that is exerted upon a loop of current when that loop of current is placed in the presence of a uniform magnetic field. Placed in the presence, I think that's how you spell presence, placed in the presence of a uniform B field. Okay, I'm going to use a rectangular loop of current here in which to demonstrate this loop of wire, for example, like so. Let's say the loop of wire is facing at us like this. Okay, let me give it some dimensions here. Let's refer to this side of the rectangle as A, this side of the rectangle here as B. Okay, let's say that the conventional current is flowing through the loop like so. Okay, there's some sort of potential difference that is causing this. I'm obviously not drawing that here on the diagram. But then we also have the magnetic field like so, pointing straight out at us like this. So the easiest way to illustrate this is with my rather crude drawing like so. The B field here is pointing straight out at us like this, and then I have my loop indicated in this manner. Okay, now this is what it looks like face on, but what I'm actually doing here is I'm going to be tilting the rectangle like so, such that it's on an angle with respect to the magnetic field, now in this direction. So this is what it looks like face on, but it's going to be tilted on an angle with respect to B. I'll draw that on the lower board in just a moment. Okay, before I do, however, let's just talk about the forces that are going to be exerted upon two sides of this rectangle, here and here, due to the magnetic field. We'll use the expression F equals IL cross B in order to do so. Okay, so first of all, this side here of the rectangle, we have IL in this direction, and we're crossing it with the B field like so, then gives us a force vector here to the right-hand side. That force is applied equally at all points here along this leg of the loop. Okay, and then similarly for this side of the rectangle here, if we do IL cross B like so, that then gives us a force vector to the left-hand side. Once again, it's applied equally at all portions here along this segment, like so. Okay, these two forces just cancel each other out. However, as I said, I'm actually taking the rectangle and we're not looking at it like this, we're tilting it at an angle like so with respect to the B fields. Now let me go ahead and draw this here on the lower board. Like so. So there is my rectangular loop. What we're looking at here are the sides A. Okay, and then I've got my magnetic field like so, pointing in this direction here to the right-hand side. Okay, let's say that this right here is the center of mass of the rectangular loop, just to keep things simple. Okay, now on the board above, let's go back to that diagram and just describe the forces on the top and lower half here, lower halves rather, of the rectangular loop. Okay, so for this top half right here, we have IL in this direction and then cross B like so. That then gives us a force upwards. So, okay, and then down here, we've got IL like so, cross B, then gives us a force downwards, like so. Okay, those forces are equal to each other, so then therefore they cancel each other out again. This then means that the rectangular loop does not translate. However, it will rotate, as we can see here on the bottom board. Because with the top of the rectangular loop, right here at this point, we have a force vector which points upwards, like so. The magnitude of that force, by the way, IL times B, is I times little b times big B for the magnetic field. Like so. Okay, same thing down here. We've got a force vector like so pointing in this direction. Therefore, once again, the magnitude of that is I times little b times big B like so. But because those two force vectors are applied away from the center of mass, this then means that a torque is going to be exerted upon the rectangular loop due to this magnetic field. We want to calculate the net torque. So there's going to be a rotation, in other words, in this direction, like so. Okay, so in order to calculate the net torque here, we have to do a little bit of R cross F. Like so. So let's take a look first of all at the top portion here where the force is applied, this distance here away from the center of mass. This right here is the moment arm. The moment arm here is 1/2 of little a from the top board. So right here like so is a over 2, and then right here is the force vector. Okay, let's go ahead and define an angle here on the diagram. We'll call the angle theta. And now if you do R cross F, you get a torque vector that's into the board. Like so. Okay, later on when talking about the energy transfer, we will make this a negative number, but for now, let's just go ahead and calculate the torque itself. All right, so that torque then, therefore, is going to be RF sine theta. So R times F times sine of theta, where right here is the force F. Times the magnetic field B. There we go. Like so. Okay, now let's calculate the torque due to this force here applied at the bottom of the rectangular loop. So right here is the moment arm. It's once again an A over 2. Like so. Right here is the force vector, and then right here is the exact same angle theta as I described earlier. And now when you do R cross F here, you also get another torque vector into the board. Like so. Once again, let's just write down its magnitude. So the magnitude here is R times F times sine theta, where the force once again is IBB. So go ahead and substitute that into here. Like so. And now because the two torque vectors here and here point into the board, this then means that they'll add together, of course, to give us a net torque into the board. So then therefore, if you place this rectangular loop in the presence of this magnetic field, the current is flowing as described and you let go of it, then it's going to start to rotate in this direction like so. Okay, so let me go ahead now and get an expression here for the net torque. The net torque is going to be this value here plus this value here. Notice that they're the same thing, so they just add together and the 2 goes away. And then therefore the net torque here, I'll just refer to it as tau, is IAB times B times the sine of theta, like so. Okay, notice the A times B. The A times B, the A times little b that is, that's the area of the rectangle. Let's just refer to that as capital A. So the area of the rectangle is A times B. And now let's write the expression like this. Okay, notice that this expression here is a cross product. It's a cross product between two vectors. What are the two vectors? Well, one of the vectors, of course, is the B field itself. What is the other vector? The other vector is this quantity right here, the current times the area. This quantity is given a name. It's referred to as the magnetic moment. The magnetic moment is I times A, and unfortunately, it is given the symbol mu. So it is yet another mu. To I times A. Okay, what is the direction of mu? Okay, it's the same as the direction of the area vector A, which for an open area is perpendicular to the area itself. The direction is described by right-hand rule. So for example, if I once again face the loop towards us like this, and the current is flowing counterclockwise on my simple diagram, then I times A, the magnetic moment mu, points in this direction like so, perpendicular to the rectangle, which is tilted on an angle. So then therefore on this diagram, the magnetic moment vector mu looks like this. Like so. Right here is the mu vector, once again the magnitude of which is I times A. The angle theta that I described in the calculations a few minutes ago is actually this angle right here. This right here is the angle theta. So then therefore torque is equal to mu B sine theta. This then means that we have a cross product. Mu cross B. This right here is the magnetic equivalent of the following that we saw back in chapter 21. Tau equals P cross E, where remember that P is describing the polarization of a molecule. That's the moment associated with a dipole, okay? Okay, this concludes here part 1 of this lecture on the torque exerted on a current loop. Next in part 2, we'll take a look at the energy transfer.